So what we're now going to do is just look at some examples of how the reactivity might differ between carbonyl groups, or how we can make things more or less reactive to start with. So the question is, which is more reactive? So aldehydes are more reactive than ketones. And the most important thing to know about the reactivity is the more electron deficient the carbon, the more reactive it will be. So whatever can make that carbon more delta positive, so anything you can do to make the carbon more delta positive, that will make it a more reactive species. Because all reactions is electrons moving from a place of high electron density to low electron density. And so the more electron density you have, the more reactive it will be. The less electron density you have, the more willing it will be or need the reaction to occur. So changing the electron density is what actually makes a reaction occur and makes it more reactive or less reactive. So why are aldehydes more reactive than ketones? Well, if we look at the structure of a ketone, the ketone has two carbons attached to the carbonyl carbon. Okay, that's lots of carbons. And what we learned from the aromatic stuff, and what you learned from the SN1, SN2, E1, E2 about stabilization of carbocations, is that carbons in a carbon-carbon bond, if there is they have the same electronegativity. So if there is a difference in the electron density due to other reasons, the electrons in the sigma bond will gravitate towards to help stabilize that positive charge. So in the ketone example, okay, you can have this inductive effect again. Through the sigma bond, the electrons in that sigma bond can gravitate towards that positive charge, because positive and negative attract one another, and it can help stabilize that positive charge. So the carbon in a ketone is stabilized more, the delta positive is less, because it's got the stabilization than in an aldehyde. In an aldehyde, ketone has two that can do it, the aldehyde has one. So the delta positive of the ketone is less than the delta positive of the aldehyde, and the higher the delta positive, the higher the reactivity. Another example would be looking at aromatic aldehydes. Okay, so if you had an aromatic aldehyde or ketone, for example, the carbonyl carbon, again, can be stabilized. So if you look here, we can think of our resonance structure that we drew before, where we say, okay, let's take the electrons out of this double bond, take them over to the oxygen. The carbon now has a positive charge. Can we do anything about that? Well, yes, we can, because we can take electrons out of the ring to form our double bond, and we can start moving that charge around the ring. So it's just another example of how you can make the carbon of the carbonyl less electron deficient. And if it's less electron deficient, it's less reactive. Okay. We are going to come back right at the very end of this to look at the key functional groups that we're going to talk about, the key carbonyls, and we're going to put them in order of reactivity. But this is just, if you had two ketones, one of them was aromatic and one of them wasn't, the aromatic one would be less reactive. So again, it's just to start getting that in your mind. This is kind of an additional and nice to know, but not essential. Right, I've talked to you for far too long now, so I've got a little question for you. So what I want you to do, there are two examples here. To make it easy for you, clearly one of them is under basic conditions, the other one is under acidic conditions. So what I want you to do now is to take those two mechanisms we've been talking about and apply them to a real example.